All right, kiddos, let's talk about ionic bonding. All of Unit 6 is about bonding, but until now we haven't actually talked that much about what bonding actually is and how it actually works. And so that's what we're going to hit in today's lesson. So first off, if you remember on our periodic table, we've talked about this numerous times, but you need to keep in mind that there's a staircase here. Okay? And again, we've covered this many times, but remember that everything on this side of the table are what we call metals. Okay? Everything on this side are non-metals. Okay? And why that's so important to us now is that we know that we have an ionic bond if I have a metal. Okay, so if I've got a metal, I have an ionic bond. It also counts for polyatomic ions, that if I have a polyatomic ion, I have a metal. But this really is sort of key and vital for us, is that if you've got a metal, then you have an ionic bond. So that's sort of step one for where we're going to go here. So that means that if I've got something like, say, sodium chloride, okay, that is going to be an ionic compound because sodium is a metal, okay? Whereas if I've got something like carbon dioxide, those two things are both nonmetals, and so therefore that's a covalent compound, and we'll talk about that in the next lesson. So metal makes it ionic, nonmetals only make it covalent, okay? So hopefully that clears a little bit up there as far as like determining which is which. Now, this diagram right here you've seen before. This is nothing particularly new, but if you recall when we did this, we were talking about how ions form, and obviously if we're going to have ionic compounds, we have to have ionic bonds. So I want to run through this whole diagram, this whole idea here again. So here's what's going on. Sodium has one valence electron. If you looked on your periodic table, okay, and counted over, sodium's right here, first column, so that means one valence electron. Fluorine is way over here, so if we counted over there, it'd be 1, 2, 3, 4, 5, 6, 7 valence electrons. And that's exactly what we see here. We've got 7 electrons in the outer shell. Now, neither one of these is happy because remember what we're looking to get to is we want to get to an octet, right? Okay, we want 8 valence electrons. So the way that's going to happen then in ion formation, if you remember, is that the sodium is going to give its electron to the fluorine. Okay? Now, here's what happens now, is that this makes this everything here happy because now fluorine has 8 valence electrons, and you're looking at sodium and thinking, well, it only has 0 now, so it's not very happy. But remember, valence is the outermost shell, so outermost occupied shell. And so if there's nothing in the shell anymore, we basically just take it away, and the highest occupied shell now is this one. And if you count those, we've got 8 there also. So both of these things are happy. Now, what does that have to do with ions? Well, here's what happens, is that now that I've lost an electron, sodium no longer has a neutral charge or a charge of 0. Okay, it's got a +1. And why is that? Because I've still got 11 protons, but now I only have 10 electrons canceling them out. So that gives it a +1 charge. So sodium gets a +1. Okay, the fluorine, on the other hand, had 9 electrons, but now has 10. And so instead of it having a 0 charge, it now has a -1 because it has one more negative than it has a positive. Okay? So that gets us to, and I'll come back to that in a second, that gets us to step 1 of ionic bonding. The first step is this right here, that we form ions and cations. And man, my arrow drawing is really bad. There, that's a little better. Formation of anions and cations. So that's what we just did, is that when you have a metal and a non-metal come together, the metal is going to give up its extra electrons, its valence electrons, to the anion, which is going to be the non-metal. Okay? Cations are always metals, anions are always non-metals, or at least usually. There are some exceptions. And then what happens is that there's electrostatic attraction between those two things. So like in our previous example, what happened is we had a sodium with a positive charge and a fluorine with a negative charge, and so those two things are attracted to each other. Opposites attract electronically and magnetically. So those two things are going to come together, and they're going to form a sodium fluoride. Okay, and that works well because they both got a positive and a negative charge. But what happens if we have things that don't have +1 charges, and so I might need more than one? So let me sort of show you how this works. So let's say that we've got something like magnesium and chloride. Let's say I want to show bonding between magnesium and chloride. Well, the first thing I want to do is I want to look at the valence electrons. So I've got 2 in magnesium, I've got 7 in chlorine. Okay, so I'm going to draw my Lewis dot structure because this is the easiest way to deal with this whole thing. Instead of drawing out all those electrons like I did in that big model that we just showed, this is the whole reason that we do Lewis dot structures. So we do like we did before. Magnesium is going to give up an electron to chlorine. Okay, so that's going to get rid of this one. And so now chlorine's got 8, so it's pretty happy, but the problem is magnesium still has 1. And in order to drop that outer level and get down to 8, it has to lose this one. Okay, now there's a relatively simple solution for that. I mean, what that solution would be is that we'll take a second chlorine. Again, me and the valence electrons, I'm telling you. Okay, so we take that second chlorine, and again, it has 7 valence electrons. And then the magnesium is going to give up its other electron to the second chlorine. Okay, so now both chlorines have 8, magnesium has 0, and remember when they have 0, it actually means that they have 8 because they drop down a level. So now everyone's happy. Magnesium now has a 2+ charge because it lost 2 electrons. Each chlorine has a -1 charge because they gain an electron. And this is how the bonding works. Now the problem is a lot of times students get confused because they set it up like this, magnesium and a chloride, they move 1 electron, and they forget that they have an extra one there. Okay, so what do you need to do then? Well, there's a simple way to always tell how many of each thing that you need. And that simple way is what we call the crisscross method. Okay, so we're going to take those same 2 things, magnesium and chloride. Okay, we're going to look at those. And what we're going to do this time, and looking on the periodic table, is instead of looking directly at valence, we're going to look at their charge. So if you recall from previous lessons, everything in this column has a +1, everything here is a +2, -1, -2, -3, all that stuff. So chlorine has a -1, magnesium has a +2. Okay? So we're going to put the charges on them at the beginning. That's a little unorthodox from what we've done so far. So here's how the crisscross method works. Okay? What I'm going to do is I'm going to take the number of the charge of the magnesium and I'm going to bring it down and make it the subscript for the anion, the chlorine in this case. I'm going to do the same thing here. There's no number given, but we know that that's a 1. And so that tells me what my final formula is going to be. It's going to be MgCl2. Now, why that's really useful to us is because if I do that first, then I immediately know when I start to draw the bonding that we just did that I need 1 magnesium and 2 chlorines. Okay? So let's try another one out just to sort of see how that works. Let's do barium and nitrogen. Okay? You look at your periodic table, you see that barium has a charge of +2, that nitrogen has a charge of -3. Okay? And so we're going to bring those down. That means I'm going to need 2, and I'm going to need 3 here. Okay? So that means if I was going to draw the bonding between these 2 things, that I would need 3 bariums. 1, 2. 1, 2. Okay, and that's the 2 valence electrons. That's where it's going to get the +2 charge from. Nitrogen, remember, has 5 valence electrons. Okay, I can never get those top electrons right. One of these days, I will. Okay, and then we show the transfer of electrons. So 1, 2, 3, 4. Okay, and so we're filling all these up. And so now the nitrogens all have 8. The bariums all have 0, which means they have 8. And so then we just go back and put the charges on them. So 2+, 2+, 2+, 3-, and 3-, and now that shows the bonding. But that would have been a lot harder to do had I not crisscrossed in the first place to tell how many I needed. Okay? And that crisscross thing is going to become real important to us when we get in the next unit, which is naming. You won't be able to find formulas unless you crisscross them. And the reason that we do the crisscross is because the charges have to balance out. Okay? For any ionic compound, they have charges, but when you put them together, they have to balance. Okay? So I've got a +2, and then I've got 2 -1s. Okay? And that's how that's going to work out. All right, so that's the 2 parts, formation of anions and cations and showing electrostatic attraction. All right, so quick definition time. The first thing that's pretty unique about ionic compounds is that they form what we call a crystalline structure. Now, what that means is that when they set themselves up, that they're not just in individual molecules like covalent compounds are that we'll talk about in the next lesson. They are in what's called a crystal. So each little spot of this crystal represents a different atom. So in this case, where it's magnesium oxide, magnesium and oxygen, I don't find like one magnesium and one oxygen together as a unit. Okay, I find a bunch of them all together, locked together in this really regular repeating pattern, that's called a crystalline structure. Okay, so when you hear the word crystal or crystalline structure, you want to think that everything's locked into this very orderly pattern. Okay, now this means that we don't actually have molecules of ionic compounds. Instead, what we have are what are called formula units. Okay, a formula unit basically is a molecule for an ionic compound, but since they don't exist like just a calcium and two fluorines by themselves, since they exist in these big crystals, then what we do is we reduce them to the lowest ratio. Okay, has to be the lowest ratio. That means you have to reduce it when you do the crisscross. So if you look back to that last one that we just did, if I had magnesium that has a 2+ charge and oxide that has a 2-, and if I crisscross them, what I really get is 2 and 2. Okay, but since it's an ionic compound, we don't have just like this. What we do is we have to reduce it if we can. And so what that's going to leave us with is MgO. That's the lowest ratio, and that's what's called a formula unit. Okay? So we saw how a couple of those worked, and the last thing we want to get to here for ionic compounds is what are the differences between ionic and covalent compounds? Not between the bonding. We'll talk about that in a second. Ionic compounds have transfer of electrons. Covalent compounds, we'll see in the next unit, have sharing. But what's the difference between the actual compounds? Well, keep in mind that the difference is always due to that crystalline structure, the fact that the ionic compounds are all very much locked rigidly into place. And so it's going to give us this. So here are the differences. At room temperature, ionic compounds are all solids. If we went in the chemical closet and I started pulling out ionic compounds, pretty much everything would be a crystalline powder or crystal flakes or something like that, but they're all solids. I could go in the cabinet easily and pull out a bunch of covalent compounds that were not in solid phase. We could pull out the gas canisters of CO2 or nitrogen or anything like that, and they would be in gas phase. We could pull out some hexanes or alcohols and stuff like that, and they're liquids, and they're all covalent compounds. Reason for that is because the crystalline structure of the ionic compounds keeps them locked together, and so it's harder. You have to put in a lot more energy to get them to change into phases other than solid. That leads us right into the next point, which is their melting point. Ionic compounds have really high melting points, and covalent compounds tend to have low ones. The easiest way to think about this is like comparing salt and sugar. If I put sugar in a pot, put it on the stove, turn it on, it's going to melt pretty easily. That's because sugar is a covalent compound. It's a low melting point, so a couple hundred degrees and it would melt. If I put that salt in the same pan and turn it up to the same temperature, it's not going to melt. I can't get my stove to a hot enough temperature to melt salt. To melt salt, you need about, it seems to me it's like 1800 or 2000 degrees Celsius. So your stove isn't going to come anywhere near it. So you might be able to burn it, but you can't melt it. You can't turn that into liquid phase without having a really high temperature. Okay? Now, what you can do to them, though, is you can dissolve them. Ionic compounds dissolve pretty well in water. And it's because they are ionic, and we'll see later because water is polar, that the polar nature of the water is going to allow it to basically pull the ions apart, and so they're going to dissolve pretty easily. Covalent compounds, they very rarely dissolve in water. There are a few, like sugar is an example that does, but a whole lot of them don't. Liquids in particular, like if I put oil and water together, they don't mix. Okay, and the last thing is their conductivity. Conductivity is just what it sounds like. It means, do they conduct electricity? Do they conduct heat? Particularly electricity in this case, and the answer is ionic compounds, if they're liquids, do, and if they're aqueous, okay, aqueous, remember, means dissolved in water, then yes, they're gonna conduct electricity. Covalent compounds don't conduct electricity very well. In fact, they tend to make good insulators instead. Okay, so hopefully that cleared up how to do the bonding and all that for ionic compounds. For the next unit, we're going to talk about covalent compounds, and you'll really see the difference between the actual bonding. But this table, you need to know this is going to be on the test. This is the difference between the compounds themselves. Thanks.